We'll see what we got here. There's a lot of aspects to the test cell, the test lab, to the entire environment that are important, of course. Not only the test cell itself, where the equipment is, but the surroundings, the supporting stuff, control and meeting rooms, where you're going to route cables and hoses and hydraulics, and how you're going to run everything. What about safety? You know, there's many different aspects that have got to be integrated into it, and it's got to be planned ahead of time so that you've got everything there that you need. So you need to think ahead. Instrumentation and monitoring, all of that stuff. Wolfgang, I'm sure, is going to talk well about reaction bases and stuff, so I'm not going to cover any of that stuff at all. I am going to talk a little more about some of the lab layout stuff. This is an example of a complete vehicle test lab. There's areas you can see down in the pit there where we can store various fixtures and equipment. There's a lot of big parts to these big test systems. They got to be somewhere. You got to plan ahead for that. So things like that have to be dealt with. How do you bring the vehicle in? In this case, it's a rail test lab, and we bring the vehicle in by rolling it in. Those T-slot tables that you see on the left side are actually have a rail head cut into them. So we can run a train right inside there, and then we use the crane over there. I believe it's a 70-ton crane. There's two of them, and we can lift the vehicle up and put it into the test cell. So that all had to be thought about quite a ways ahead of time to get the foundations in for the cranes and get the power, get everything planned ahead of time. So it was an interesting and definitely a kind of an exciting time. Lots of different types of test cells, test labs, because the specimens are very much driving it. Here, they've got a huge variety of stuff available that they can test. A lot of heavy vehicle things. You got a tractor in the next room, but you see their labs are open. They're able to get access to them, bring in this heavy equipment when they need it. It's pretty well thought out. Running wires, cables, and hoses sometimes isn't done very well. It's definitely worth planning just a little bit, and I'll admit that MTS is not always as good at this as we should be. It's one of those things that kind of gets left to the end, and sometimes it doesn't get attended as well as it should. But it is important. There are a variety of ways to neaten these things up. It's not a question of spending a lot of money. It's a question of spending some time to think about it and take the time to implement it. That's the big drivers. The other thing I'm going to talk mostly about today is hydraulic flow, hydraulic distribution, hydraulic dynamics. In my travels around various test labs around the world, I see a lot of people having problem with their hydraulic system. And the reason for that generally is that the distribution system wasn't well planned. So let's talk a little bit about the hydraulic distribution system. First of all, its main function is to get oil from a pump of some kind to your system with as much pressure as possible available to run the servo valve whenever it's ready to open. That's our main goal. So that requires several things. First of all, it requires a steady state flow that's approximately average flow. That's what the pump provides. So with the average flow running through those pipes, a certain amount of pressure is required to get the oil to the systems. And so we did an analysis. This is an example here where the white boxes with the black letters talk about the total oil flow in each pipe. So once we know the total oil flow in each pipe, we know the length of that amount of flow and that size of pipe, we can calculate the flow losses. So we can calculate the losses to each of the systems in the laboratory if everything is running at nominal values. And that's what you see in the red numbers. You know, in the far corners, we're dropping, about 10% of our total power just to get oil to the system. Back in closer to the pumps, of course, we have much lower pressure drop. So ideally, we want to put our high demand systems as close to the pumps as we can and put our lower demand systems a little farther away so that they can tolerate a longer distance and they don't draw as much oil. So little things like that can make quite a difference. Trenches and stuff like that don't just have to be big enough to hold the pipes. They have to be big enough to work in and swing big wrenches in and drill anchors in. Please plan ahead. Wire trays and wire troughs are something that are often neglected, and they're very valuable. It's nice to have a place to drop the wires onto that's not down in the bottom of the trenches and the oil and the dirt and the stuff. It's getting in the more modern systems, we're getting to have fewer and fewer wires. At some point, it'll all be wireless, I'm sure, but we're a ways away from that. For now, we still have to worry about wires. If you neaten up your hardline system in your laboratory, you plan it a little bit, you think ahead, you can have a very safe, easy system to live with. That's what counts, and that's going to pay back for you every day you use it. So it's worth the time to think about. Don't forget about putting flexible hoses in places where there will be motion, such as when you move from your concrete of your main slab to your reaction base. That base will move some. It's got to have a flexure capability in your hydraulic system. So typical hydraulic distribution system, here's a schematic where we've got some big hardline, or some big accumulators somewhere back by the pumps. We've got some hardline system, then we've got service manifolds in each of our test cells, and there are actuators. They have some accumulators on them. Then we have some pipes and hoses to our actuators. We might have some further accumulators on the actuators. Then we've got a servo valve, and then we've got our actuator itself. So we talk about how do we pick those systems, how do we size those accumulators and put them in the right location to get the dynamic oil flow that we need. It's a very important process. There's various accumulators are at different places in the system, and so they do different things. First of all, we have to understand what are the accumulators doing for us. The accumulators are evening out the dynamics in the oil. The servo valve is opening and closing like crazy. The oil is accelerating and stopping and accelerating and stopping. The first thing you have to think about is the oil doesn't go back and forth. The oil always goes from the pump to the actuator, and from the actuator back to the pump. That means the oil has to accelerate to full velocity and back to zero every time the servo valve cycles. That's acceleration. Accelerating the oil has mass. F equals ma. That means that I'm going to have pressure on that oil that I don't have at my servo valve to do work. The dynamic loss is often ignored. You look at the equations at the bottom here, and you start to notice that there are a lot of squared functions there. Those dynamic pressure losses get to be very high, very fast, and yet they're largely ignored when people size their systems. Accumulators can help with that because that oil can't get to my servo valve now. It's got to get accelerated and moved. But if I've got an accumulator close to my valve, it doesn't have to accelerate so much oil mass. It can move faster, and it can get that oil to my valve while the oil in the pipe is still accelerating and coming in, and now it can fill that accumulator again. You start to see how critical these accumulators are in making the system work well. There's generally at least 3 different sets of accumulators on each system. There's the main hardline accumulators that are usually on the wall, often where the piping system comes into the lab, for example. They can be 5, 10, 20, sometimes even bigger. Some labs we have several thousand gallons of these accumulators on the hardline, especially for great big systems like seismic systems, where they run the pumps for 2 or 3 days and charge the accumulators, and then they run their 2-minute test and they blow it all off. Then we've got HSM accumulators, hydraulic service manifold accumulators. They tend to be in the order of 1 to 5 gallons. They're closer to the actuator, but still separated by hoses. Those hoses have the same problem. That oil has to accelerate, get to the servo valve, and it has to decelerate. And to do that, it loses pressure. It loses the capability to do work. So when people tell me, oh, yeah, I want a 10-meter hose to my actuator so I can move it around the lab, you know how much performance you're going to get out of that hose? None. Let's talk. If your hoses are more than 3 meters long, they're too long. I'll bet nobody sat down and figured out what that means to your performance. Do some calculations, the equations are there, and it'll open your eyes. You'll be looking at needing accumulators and shorter hoses pretty fast. And if you don't do that, people complain the hoses are jumping around, I don't get good signal quality, the lab is noisy. It's because you don't have good hydraulic dynamic control. Close coupled accumulators, that's your high frequency last line of defense. They're small, but they can give you a little bit of oil right now because it's not separated from the servo valve by inertia. Boom, it's right there. It's kind of interesting, by the way, accelerating the oil through the neck of the accumulator, you see the small diameter port, that's a bell crank ratio. That magnifies the inertia of the oil by the diameter of the accumulator to the diameter of the port ratio. And that's a squared thing. So if the accumulator is twice the size of the port, the ratio is 4 to 1. That means that the oil that has to be accelerated out of the accumulator looks like it's 4 times as much mass. We've started to put some accumulators on systems with high performance with no port. The piston is wide open to the servo valve all the way, so we don't have all that acceleration in that neck down port to deal with. Interesting stuff. Of course, it's important to know where you're going to put your accumulators on your hardline, because there has to be ports on the hardline for that. So here, this is a case, an example where we laid out, this is where we're going to want these accumulators on your hardline, so that hardline's got to be ready for those accumulators. We've got to have bracketry on the wall. We've got to have space for them. We need to have nitrogen in the laboratory to keep them charged. It's a whole system. We've got to plan for it. These big accumulators on the wall are a long way from the servo valve. And this inertia thing is going to isolate them. They can't provide help for me at higher frequencies, because that oil can't get from the wall to the valve. So the accumulators, the great big ones on the wall, provide this low frequency stuff you see in the second graph there, large hardline accumulators. But then they start to roll off pretty fast at about 2, 3, 4, 5 hertz. They're not helpful anymore. That's when the HSM accumulators kick in. They're smaller, but they're closer. The inertia is less, and they can get that oil to the valve a little faster, so they take care of the middle frequencies. And then we got this close coupled ones. They're right at the valve. That takes care of our high frequency supply. So the pump is providing only the DC supply of oil, the low frequency oil. All of our dynamic oil flow is coming out of our accumulators. It's not coming out of the pump. And the highest dynamic flow in the system is between the HSM and the valve. And the lowest dynamic flow in the system is the pipes in the wall. Most people do not look at it that way. Another thing, what about return line pressure? If I've got accumulators, I've got nitrogen, I've got some sort of piston or bladder. When I put nitrogen in it, it goes to the bottom and it closes itself off. Until the pressure in the line is more than the precharge pressure, the accumulator is completely blocked off. It doesn't exist. If I don't have, say, back pressure on my return line to put like 3 or 5 bar on there, my return line accumulators aren't there. They're not working. And then a system makes a lot of noise and banging, and there's problems. I've even seen one facility where they're starting to crack the corners of the hardline. It's been shaken so bad the paint's coming off. I don't want to work there. So a little bit of planning, a little bit of thinking, a little understanding of the dynamics, and you can get a lot better performance out of your servohydraulic system. There's differences between piston accumulators and bladder accumulators and diaphragm accumulators. The differences are not such a big deal to most applications. For some special applications, they are important. What's important is that they're big enough and they're in the right place. That's what's most important. So life is good if we're running sine waves. I can calculate exactly how much accumulator I need because I know all of the characteristics of the waveform. So I can predict how much oil, how much accumulator I need and where I need it. But our world is real-time data. It's not sine waves. It's these spikes we get at the end, and that makes accumulator sizing much more challenging. If we take a look at a real-time lab flow, the top line shows the pump flow, and the bottom line shows the actuator flow. Big difference there. Everything between those two comes out of the accumulators. How do the accumulators work? Well, the blue line here is the pump. And the black line is the actuator demand, the servo valve demand. So when we go above what's there, we're getting that oil out of the accumulator. When we're below what's available, we're recharging the accumulators. In, out, in, out. You can see the model there. So I've got to have enough accumulator volume to handle that difference in flow. Now you think about that, okay, gee, that's not much, is it, Steve? It's only a quarter of a gallon, 0.25 gallons, a liter. Yes, that's how much real oil I need at full pressure. That means the accumulator has to be much bigger than that to provide that oil at the pressure I need it. My rule of thumb is that if I need a liter of oil out of my accumulator, I need at least a 10-liter accumulator. Bigger is better. There's no such thing as too much accumulation. And there's lots of too little accumulation. Just trade-offs with precharge pressure. One of the ways you can get more accumulator in your lab is increase your precharge pressure. If you're running a 210 bar, the optimal tuning point is about 140 bar, not 70 bar where most people charge, just as an option. Twice the precharge pressure basically takes and doubles the available oil I get at pressure out of the accumulator. Cavitation means that the pressure in the line somewhere is dropping so low it's vaporizing. It boils for an instant and collapses and destroys the oil and the pipes and the whole thing, and it'll actually etch away servo valve steels and things like that. That's another reason sometimes we want back pressure on the system. If we can't get that spike taken care of with enough accumulator, when my valve closes, you have to realize it's at the end of a pipe with all this oil flowing, full velocity, and now the valve closes. What happens to that oil? It's moving. It's got inertia. It's going to drop that pressure at the servo valve really bad. It's going to cause cavitation. Unless we can provide some makeup oil while that oil decelerates and stops moving. That's what the closed coupled accumulators do for us. That's why they're so important. And sometimes we have to back pressure the system just to raise the pressure up because we can't change that dynamic, but we want to get it above the cavitation problem. If you want further explanations on this stuff, please feel free to contact me. There's no problem. It talks about how the accumulators work. You have to think about the fact that to get oil out of it, the pressure has to drop. That means I can't have 210 bar in my system all the time. As soon as the valve opens, that pressure will drop. How much it drops is a question of how well I've designed it. If I've done a good job, it'll only drop a few bar and I won't even notice it. If I haven't done a good job, I've seen labs where it drops 70 or 150 bar when the valve opens, and they have really lots of problems. These are just cheater equations to make it easy to calculate flow dynamic things and stuff like that. Strong floors and reaction bases, and this is the stuff that builds up a useful test lab. It's in the details, and they need to be figured out before you break ground and pour concrete. So that completes my prepared presentation. Thank you very much.